So my screen is visible, right?
Yes, ma'am.
Okay. So hello everyone, myself Chinmoy Datta. I'm a PMRF scholar at IIT Madras, and I'll be taking the class of Advanced Machining Process, which is instructed by Professor Manas Das from IIT Guwahati. So maybe someone wants to join. So we'll be taking the class of Advanced Machining Process. So material removal process of any material is done by mainly two processes. One is conventional process and one is non-conventional process. So in conventional process, turning, milling, grinding, those methods are following. So in non-conventional processes like ultrasonic machining, abrasive water jet machining, those methods are coming. So conventional machining processes are used from years ago, but why in suddenly non-conventional machining process came into our picture. So conventional machining served the purpose and requirement of industries over the decades, but new exotic work materials, and also we can say advanced engineering materials, those and complex geometric design of product and components were putting lot of pressure on capabilities of conventional machining process to manufacture the components with desired shapes and economically. And also one thing we have seen, like in conventional machining process there is interaction between tool and workpiece, which may damage the workpiece surface as well. So that's why for complex geometrical shape and for difficult to machine materials such as advanced engineering materials such as titanium, aluminum alloys, so non-conventional machining process came into our picture. In non-conventional machining techniques, there are mechanical based, electrothermal process based and electrochemical process based machining process are there, and there are sub parts in each processes, like in mechanical based process, ultrasonic machining, abrasive jet machining process, water jet machining and abrasive water jet machining come into our picture. So in first week, as maybe you have gone through that ultrasonic machining, or maybe some of you have idea on ultrasonic machining processes as well. So then also I'll give a brief idea on ultrasonic machining, that how it works. So like in ultrasonic machining, a tool of desired shape vibrates at an ultrasonic frequency, that is approx 19 to 25 kilohertz, with an amplitude of around, you can say, 15 to 50 micrometer over the workpiece. Generally that tool and is pressed downward at the feed force F, we can say. Then between the tool and workpiece, the machining zone is flooded with abrasive particles, which can be at water-based slurry also. As the tool vibrates over the workpieces, the abrasive particles acts as an indenters and indent both the work and tool material. So the abrasive particles, as they indent the work material, remove in same manner. So we'll see in what ultrasonic machining in ultrasonic machining, mainly the brittle materials are cut by this process, because in brittle material, due to crack initiation or propagation, the brittle fracture occurs in the material. So material is removed in that portion. So maybe so actually in brittle materials which are poor conductors of electricity, so those materials maybe can't be able to machine by ECM or EDM processes. So this method is suitable for cutting brittle materials also. So the applications we can say, like cutting hard and brittle metallic alloys, semiconductors and ceramics. So as I have discussed, in ultrasonic how it works. Someone maybe join. Okay. So as we have seen how ultrasonic machining works, so there are the process parameter which are like, as I have told, like amplitude of vibration should be around 15 to 50 micrometer, then frequency will be in between 19 to 25 kilohertz. Abrasives which we are used in ultrasonic machining process, those are SiC, L2O3, B4C and diamond, and abrasive size also fall between 15 to 150 micrometer. So the mechanism, as I have been mentioned, the working principle of USM. USM is generally used for machining brittle work material, as I have discussed. Like material removal primarily occurs due to the indentation of the abrasive grids, and during indentation, due to the contact stress, crack would develop just below the contact zone. Then as indentation progresses, the cracks will also propagate due to the brittle fracture or increase in stress, and ultimately lead to the brittle fracture of work material under each individual conditions. Like thus the tool are made of tough, strong and ductile materials. See, the USM can cut brittle materials, but the tool should be made of ductile materials, such as we can say stainless steel and other ductile material alloys. So other than this brittle fracture of work material due to indentation, some material removal may occur due to the free flowing impact of abrasives, which are used, the abrasives are used as SiC, L2O3, B4C, those materials. And to be rather in thus in the current method, material between tool and workpiece followed by indentation and brittle fracture of the workpiece, it considers the deformation of the tool also. So like as I have discussed, we can say the question, the answer of this question is, what is the material type of tool and workpiece used in USM? Can anyone tell, like as I have discussed now only, so you can tell also like the material type of the tool and workpiece. Maybe you can put it in chat box as well. So what type of material is used for tool material and and what type of material is used as workpiece surfaces? Can anyone tell? Maybe you can put the answer in chat box itself. So the tool type of material is ductile, right? Like stainless steels and other ductile material alloys. And workpiece used in USM is brittle materials. Why? Because those will undergo in brittle fracture due to the indentation. Okay. So in USM process, like which type of material? Okay, that brittle material. In ultrasonic machining, the material is removed by, can anyone tell? See, by if I give option as like by abrasives also, right? So by the flow of abrasives. The abrasives used are SiC, L2O3, B4C. Those abrasives are only removing the material. Okay. So now come to that ultrasonic frequency part. Like, so first we'll like discuss on the transducer part. So the ultrasonic vibrations which are produced by transducer. So what is the working principle of transducer? See, the transducer is driven by some suitable signal generator, like followed by power amplifier, and like it used as like electrical energy of high frequency is converted into mechanical vibration through transducer. in that USM machining process. So like the transducer for USM works on following principle. One is called piezoelectric, one is magnetostrictive, and one is electrostrictive effect. So magnetostrictive transducer, like we can say, used in most popular when robust amounts, all like piezoelectric also may be used in USM. Those two methods are only used in ultrasonic machining. So the like electrical energy of high frequency converts into mechanical vibration through a transducer, and then mechanical vibrations are transmitted to abrasive particles in the slurry via an energy focusing device, or we can say that energy focusing device we can say as horn or concentrator. Also in ultrasonic machine you can see like that energy focusing device is called like tool horn or tool assembly concentrator. So some of the properties of piezoelectric effect are like high energy, it has high energy efficiency, no cooling requirement is needed, like no heat damage liability itself, like and low power capacity. In magnetostrictive also we can see some properties of that magnetostrictive transducer, that is like high power capacity, but the main drawback we can say of magnetostrictive transducer is it is having low efficiency. So we can answer this question, right? In ultrasonic machining, the function of transducer is to, can anyone tell? You can use your chat box also. I have discussed it, right? So the function of transducer is to convert electrical energy of high frequency into mechanical vibration. Okay. So coming to that vibration and like vibratory waves and ultrasonic frequency. See, when we'll call it ultrasonic frequency, vibratory waves which are having frequency greater than upper frequency limit, that is equal or greater than 16 Hz of the human ear, that is called as ultrasonic frequency. So types of waves created due to ultrasonic frequency may be longitudinal waves and shear waves, but shear waves is neglected in ultrasonic machining process. So longitudinal waves are mainly used in ultrasonics, and because like it's easily propagate in solids, liquids and gases. So we have to remember like in ultrasonic machining, like longitudinal waves are only used as ultrasonic frequency wave. So from that discussion we can say like amplitude of vibration is having a great effect on ultrasonic process, whole process and whole material removal process even. So we can answer this question which is given as which process parameters is the most significant for linear material removal rate. So we have seen, right, in ultrasonic frequency even vibratory waves are creates due to longitudinal waves, and this amplitude of vibration plays an important role in material removal rate in ultrasonic machining process. Okay, then moving to the next part. Okay, so you can see the diagram, right, of grit and workpiece tool, how the grit and workpiece tool and grit interacts in ultrasonic machining process. So this is the geometry of that grit and workpiece tool interaction. So from that diagram we are seeing like dB is the dia of abrasive, and like there are some equations or relation we can say in between indentation, like indentation depth, number of abrasives in contact with the job or say workpiece surface, and abrasive grid dia. So like dB we can say like dia of abrasive. So and n will this n is number of abrasives which are in contact with the workpiece surface, and F is frequency. Okay, so from like diameter of abrasive, number of abrasives which are in contact with the workpiece surface, and frequency, if we know those parameters, we can calculate the material removal rate mathematically by given formula, that MRR equals to 2/3 pi dB into indentation, delta W is the indentation depth, to 3/2 power of into n to f. So from this, like you can even solve the numericals which are given like in texts. Okay, so like if A is the total surface area, this A is the total surface area, and C like and the surface area of the tool facing the workpiece, then the volume of the abrasive slurry of 1 grit thickness we can say like A into dg. dg is the diameter of grit, dia of grit. Dia of grit. So A is the total surface area, dg is the diameter of grit. So we can measure where we can calculate n, number of abrasives which are in contact with the workpiece surface. The and that C is the actually concentration of abrasive grits. So from that equation, like we can say that concentration of abrasive grits is related to pi into dg cube into n divided by 6 equals to A into dg into C. So if we solve solve this equation or like simplify the equation, we'll get n, number of abrasives. So if we consider every parameter like dB, which is abrasive dia, delta W, which is indentation depth, n, number of abrasive, f, frequency, C is the concentration of abrasive grits, dg is the diameter of grit. So we'll get like f is the frequency, as I've said. So we'll get like and even the indentation will be like inversely proportional to the flow strength, that is lambda will be delta T by delta W. Okay, so from these equations also, if we simplify the equation, we'll get this formula of MRR. So MRR is dependent on C, A, dg, F, mu. F is the maximum force, and M, A, C, and delta W, lambda. So in each parameters MRR is dependent. So the number of impacts on the workpiece by abrasive grits in each cycle is dependent upon, as I have discussed now, like from the diagram itself you can tell like the number of impacts on the workpiece by abrasive grids in each cycle is dependent upon. Can anyone please answer? So obviously it will be the diameter of abrasives, right? Okay. So a simple numerical is there. So we'll be solving this numerical right now. Like, using that previous formula of M error, where we have seen that M error is dependent on certain parameters. So that formula only we'll be using. So glass is being machined at MRR of 5 mm cube per minute by SIC. Abrasive grids having a grid dia of 120 micron. If 80 micron grids will be used for further machining, what will be the M error? Very simple. Like MRR is proportional to dg, that is diameter of grid. See, from this equation only we can tell M error is directly proportional to the dg, diameter of grid. So from this we can write M error 1 by M error 2 equals to dg1 by dg2, right? So first M error is given, right? Glass is being machined at M error of 5 mm cube. So 5 is given. Then M error 2 equals to dg1, that is 120, and dg2 is 80. So what will be the M error if 80 micrometer grid size dia abrasive grid is used? 80 into 5 divided by 120, right? So if we solve these, okay, 10 by 3, it's approx 3.3 micron mm cube per minute, because the unit of M error is millimeter cube per minute or millimeter cube per second, whatever you tell. So it will be like M error will be 3.3 millimeter cube per minute. Okay, is it clear? So if you are having any doubt, you can use your chat box. Yeah, okay, already you are telling the answers. Okay, yeah, 3.33. Okay, if you are having any doubt, you can use chat box. I'll try to answer. So moving to the next part. See, so like actually material removal is mainly occurred by throwing and hammering action. So like other modes of material removal also are present here, like as we can say, like due to cavitation, due to chemical action, but those are actually neglected in the while considering the mathematical formulas and while considering the calculations of M error. So mainly we will be considering throwing and hammering action. So as we can see that hemispherical diagram, as I have drawn here, spherical diagram I have drawn here. So that like from the diagram itself we can say that radius of the spherical like crater formed due to the fracture, like this spherical crater radius is small r. We can denote as r, assume it as a r. So a radius like capital R, which is, just a minute, this capital R in terms of grid radius and depth penetration is h. So from this like triangle only we can write the equations, right? R square equals to capital R square minus R minus h, where h is the depth of indentation, okay, and r is the grid radius, and smaller is the radius of spherical crater. So if we simplify this equation, what we'll get? R square, someone maybe to join, okay, so R square minus capital R square and plus 2RH minus h square. So we can cancel it out, r square, left is 2RH minus h square, but we can ignore this term as it's very small with respect to 2RH. So we can write approximately r square is approximately equals to 2RH, okay. So now like volume removed per grid per cycle, if we denote it is a Vg, then it will be as, see, you can even imagine like how much volume will be removed per grid per cycle. Half into 4 by 3 pi r cube is the volume of sphere, right? So half 4 by 3 pi r cube. So if we simplify or like rewrite this equation, then we can write as 2 by 3 pi into 2RH into power 3 by 2. Why we are rewriting this? Like we want to like add this value like 2RH into this equation so that we can simplify it further. So we have just rewritten it in this form, like 2 by 3 pi 2RH to the power 3 by 2. So we can write it as h d to the power of 3 by 2, and other terms we can put it as a constant k or say k1, okay. And h already we know that indentation depth, and d is the like diameter of grid, or dg we can denote it as, okay. So like if now if we denote number of impact per cycle as n, capital N, so we can say like n will be inversely proportional to the cross sectional area of the grid. That means d square or dg square. So n will be inversely proportional to d square, d minus 2. Okay, so those equations will be helpful for solving the numericals. That's why you have to be you have to keep in mind those equations, like how it's coming from, by throwing and hammering action, how it's coming as r from r square to equals to 2rh, then how volume removed per grid per cycle is calculated. Actually our aim is to calculate is MRR per cycle. So first we'll calculate volume removed per grid per cycle, then we'll be calculating MRR per cycle using that number of impact per cycle equations and that relations between number of impact and cross sectional area of the grids, that is abrasive grid size. But now the question is, while machining process or while removing the material, is every grid will be active, or say the number of we can even say probably, or you can use probability that and we can denote K as number of abrasives, or number of grids which are active or which hits the workpiece and remove material, right? So we can denote it as a K. Then MRR per cycle will be this one will be K into Vg, which we already have calculated, into number of impacts, that is n. So if we simplify this or put all the equations, like Vg equals to Hd into 3 by 2 K2 or K1, and then n also we have seen, we can write K2 into d to the power minus 2. So here we will be writing as K into K1 into K2 HD 3 by 2 into d by 2, d minus 2, or 1 by d square. So from these we can write this relation, MRR per cycle will be then proportional to root over h cube by d into f, where f will come into picture, that is frequency, and h we know indentation depth, and d is the dia of grid, right? So using this relation, if we say if frequency is varied, so how MRR will be varied? MRR will be directly proportional to frequency, and MRR also will be directly proportional to h also. So we can say from this equation we can solve the numericals. So any doubt, if you have any doubt, you can ask or put it in chat box, so that here also, so that tutorial questions which are given in previous year assignments, those I have written actually. So we can say what is the so first question is, what is the material type of tool and workpiece used in USM? We can say tool material we can use as brittle material, and ductile material, and workpiece is used as brittle material. And then in USM process, which type of material can be easily machined? So obviously that brittle materials can be easily machined using USM process, and in ultrasonic machining the material is removed by abrasives. The abrasives which are used as SiC L2O3 before C. And then in USM, what types of waves are used? We can say longitudinal waves. Why? Because like in USM process, that shear waves are neglected, and in longitudinal waves which can easily propagate in solids, liquids and gases. Okay. And in ultrasonic machining, the function of transducer is to convert electrical energy of high frequency into mechanical vibrations. Okay. Which process parameter is the most significant for linear material removal rate? So the process parameter, which process we have seen also this process parameters, right? Amplitude of vibration, frequency of vibration, abrasive size, abrasives. Among all the process parameter, amplitude of vibration is having a high effect on the material removal rate. Okay. So as we have seen that the abrasive grid size is as denoted as dg. In each cycle is dependent on dia of abrasives. Okay. Number of impacts on the workpiece, like n, which is denoted as n, and abrasive grids, which is denoted as dg, which is highly dependent on dia of abrasives. Okay. And also we have seen these equations or these relations between MRR and that all the parameters as concentration and area, and then dg and f, frequency and indentation depth, and all the parameters. So from these equations also we can say that how MRR is dependent on the other parameters. Okay. And one more thing, actually, that basic mechanical structure of USM is very, actually you can say that it's very similar to drill press itself. However, it's additional features to carry out ESM of brittle materials. The workpiece, you can say the workpiece is mounted on vise, which can be located at the desired position under the tool using a 2-axis table. So the table can further be lowered or raised to accommodate work at different thickness. So that actually the typical elements of USM are one, we can say slurry delivery or return system. One is feed mechanism, to provide a downward feed force on the tool during machining. While machining the surfaces in USM process, it should provide a downward feed force on the tool. So that feed mechanism is there. And the transducer, which we have seen already, that the working of transducer in USM process. And last is the horn or concentrator. What is the effect of that horn, or what is the function of that horn? Horn or concentrator actually amplifies the vibration to the required amplitude. We can also will see in USM process that without amplification or with amplification, what will be the frequency? With amplification, frequency will be 10 times greater than without amplification. So that's why horn plays a great role for amplifying that transducer frequency, which is 10 times greater, and so required amplitude to reach at required amplitude of in the range of 15 to 50 micrometer. And it also accommodates the tool at its tip actually. So and that then comes the ultrasonic vibration also is a great effect on this, which are produced also only by transducer itself. So we have seen the effect of magnetostrictive piezoelectric transducer itself. So those we have seen the drawbacks of magnetostrictive as it has low efficiency, but piezoelectric is also having higher energy efficiency, and also extra cooling effect is not required, but it is having low power capacity also. So those methods we have seen, those two techniques are only used in ultrasonic machining process. So and that vibratory waves we have seen, like how it affects like as longitudinal wave. Then that equations of emerer and grid diameter. Then that simple numerical we have solved, where like we can also provide that question as if say depth indentation, which is delta W, indentation depth of workpiece, indentation depth, like if it varies, then how emerer will be changing. So we can say emerer is inversely proportional to delta W. So if delta W like increases, emerer will be decreases, or we can say as like if delta W decreases and emerer will be increases. So those are the relation between, or say we can say even that relation between the maximum force, also like that the tool impulse force, like that F impulse of force on the tool and the workpiece actually is balanced. There's so the total force also we can measure from this given equation actually. So I'll write it here. So that total force, like we can measure it as N, that is number of abrasives, into F into half of F into tau. F will be the maximum force, maximum indentation force per abrasives. You have to remember like that F which is provided as maximum force, indentation force per abrasive. Okay, so if we consider those parameters, we can calculate that the total force while machining. So tau is the torque. So if the tool is being like forced, and then F is the downfit force, then we can say it as F equals to N of F into half F max, that is maximum indentation force, into tau. Okay, so like if flow strength of work material is taken as delta W, this is the flow strength, okay, this flow strength is taken as delta W, then F max we can rewrite as delta W into pi x square. X we can denote as radius, like so. Then we can rewrite this equation as F, we'll just put this value in F max. So F will be half into N F delta W, which is flow strength, into pi into x square, and then like will be delta W plus delta T, that is both like flow strength on workpiece and tool also will come into picture, and then 4 of A0. Okay, so this will be the equation of the force with which the tool is fed actually. So that is F. See here in this emerer is also dependent on that force, which is called as the force which actually the force with which the tool is fed. We can calculate using this equation also. Okay, so if like next part actually, even here also we can say Like if A is the total surface area of the tool facing workpiece, then the volume of abrasive slurry of 1 grit thickness will be A into dg, okay, of 1 grit slurry. This is the volume of 1 grit abrasive slurry. So we have used suppose we have used n numbers of grits, so then total volume of n grits for 1 grit it is a dg, so that for total volume of the n grit will be pi into dg cube into n by 6, which I have written here. Okay, this is also equals to a dg into c, where C is the concentration of abrasive grits. Why we have to take care of all the parameters? Because all the parameters are affecting material removal rate or in USM process. Okay, so this equation is very much important for calculating, like or for solving the numericals. Okay, so even that it's expected that the indentation will be inversely proportional to the flow strength, that is delta W. Okay, so MRR also we can write in this form as it's a volume of material removal. We can denote this parameter as this, and into N into F. Okay, so this is 4 pi AC into pi dg square, which I have calculated, F into dB into delta W, which is the flow strength, into 3 by 2 into in power 3 by 2. So if we simplify this whole equation, we will get MRR, these equations. Okay, so and this is the equations which we are getting through hammering and throwing action. Actually, for getting that indentation depth H, we are having two models, like one is throwing action model, one is hammering action model. So from using those models only, we'll be like estimating that indentation depth H. Okay, so that for getting those relations between that volume removal, that is Vg, number of impact and cross sectional area of grit, we have to first consider the crater sphere. From this crater sphere only we'll be calculating those R, will be creating one relation between R, capital R, small r, and H. So using those that equation only we'll be calculating Vg. Okay, that is volume removed per grit per cycle. So and from that only number of impact per cycle, and as we have seen one question also in assignment, that how number of impact per cycle, what is like how it's affected or how it's dependent on like abrasive grits. So we have seen here from like a number of impact per cycle is inversely proportional to the cross sectional area of grit, that is diameter of grit is there, which is inversely proportional like to the N. So we can say that N is dependent on the diameter of abrasive grits. Okay, so if we simplify those relations, we'll get MRR per cycle also. So from these equations we can estimate those. Okay, so if anyone having any doubt, you can ask. I'll try to solve. So anyone having any doubt or any questions? What actually I'm not getting you. What? Can you repeat?
Assignment
What? Can you please loudly tell? Actually, I'm not getting you.
assignment questions and the answer.
Yeah, actually, previous year assignments questions I have solved actually. So those are the questions which are there is in previous year and like lectures, NPTEL lectures for assignment 1. So if you go through that lectures and if you go through the process parameters, working principles and all the equations, you will be able to solve this year assignment questions as well, because those are very related to the lecture notes. So you can go through it and you can answer those questions, because basics I have explained, and I have also explained the previous year questions which are there in that previous year assignment 1. So you can take those as reference and you can solve this year assignment also.
Thank you.
So any other doubt or questions? Otherwise we can leave also. So any doubt? So shall we close the meeting? Okay, thank you.